All right, this is part 4 of chapter 11. This is all about action potentials, how we trigger action potentials, how action potentials are different from graded or local potentials, and then how do we have increased sensitivity or increased strength of our stimulus. In other words, how can we decipher intensity of a stimulus if all action potentials are relatively the same? So let's start out first with what is a graded or local potential. So the easiest way to understand it is simple, is to understand that right here. So I'm just gonna move up the chart a little bit, and what we're gonna see is that this is a chart that we saw in chapter 9, where you have a full out movement towards threshold, and then after you hit threshold, voltage gated sodium channels open, so you depolarize, and then the voltage gated sodium channels will start to inactivate and then fully close, right, later on. But at this point, voltage gated potassium channels fully open. Potassium exits a cell. As potassium exits a cell in mass, you start becoming more and more negative as you lose more and more potassium from that region of the axon, and potassium exiting makes you more negative right here. And then you kind of, those voltage gated potassium channels open a little bit too long, and you become slightly more negative than you should. Now, we'll come back to the rest of this in a second, but the reason why I'm showing this chart right here, right now, is because I wanted to show everyone that all of this kind of first movement towards threshold, that is what a graded or local potential is. Now, a graded or local potential then will allow us to hit threshold and have a full out action potential. Or if the stimulus isn't strong enough, then the graded potential goes from minus 70 to minus 56, not minus 55. When that happens, it just goes all the way back down again. You don't have a twitch, you don't have any sensation, nothing happens because you didn't hit threshold, right? So that first initial movement from minus 70 towards threshold, that is what we call a graded potential then. So a graded potential right here is triggered by a small release of a ligand. That ligand can bind to its receptor on the other postsynaptic membrane. And if there isn't enough ligands released, then you just have a small increase from minus 70 to minus 60. At that point, then it fizzles out and it comes back down. You didn't hit threshold, and because you didn't hit threshold, then nothing happens, right? So some local or graded potentials are not strong enough to hit threshold. When that happens, it just fizzles out, nothing happens. There's not a twitch, nothing occurs in terms motor-wise. In terms of sensory-wise, it's not like you feel just a light touch. No, you feel nothing. The reason why is because no action potential is triggered, because you don't trigger threshold, you don't hit threshold and have at least one action potential, right? So this can result from a few different things, in other words, right? So graded potential is that initial rise in membrane potential from minus 70 towards a threshold. So what can cause that initial rise? It can be caused by a ligand being released from one presynaptic neuron, and then that ligand binds to postsynaptic neuron. If there isn't enough ligand release, then you don't have a strong enough local potential to hit threshold, right? So local potentials can lead to action potentials, but not all of them will lead to action potentials. What else besides ligand can cause this slight movement up? Mechanical stimulation, stretch receptors, right? The more you stretch the stomach from eating food, the more stretch, the more stimulation, the more you send the signal to the hypothalamus that you're full. So mechanical stimulation, like stretching, can trigger that initial rise towards threshold. If the stretch is strong enough, those stretch receptors then stretch, right? And the more stretch, the more sodium entrance, the more likely we're to hit threshold and send a stretch signal to the nerve then it goes to the hypothalamus, telling the brain that you have slightly moved that stomach, and the stomach has kind of, right, stomach has stretched a little bit. It might not stretch enough for us to actually activate our satiety center, but it does tell us that it's stretched, so you're eating something. Temperature changes. Spontaneous change in permeability, like the autorhythmic cell in the cardiac muscle, our SA node, right? So SA node, once you hit minus 60, immediately some kind of, right, we call them funny sodium channels open up. The sodium then comes in immediately and then allows you to hit threshold, right? So a lot of things can trigger a graded or local potential, including, like we mentioned before, release of neurotransmitter, a ligand, stretch, mechanical stimulation, temperature change, or even in the SA node in the heart, spontaneous changes. Now, we say they're local or graded because they can add to each other, and the stronger stimulus, the more likely you are to then have the ability to hit threshold. So they're graded, and that magnitude varies from small to large, depending on stimulus strength or frequency. Meaning what? If you have a small meal, you may not feel full because you might not activate enough of that stretch stimulation. So then your hypothalamus activating your satiety center will tell you're full. Small meal. If all you're eating is, I don't know, a salad and only salad for your diet, well, that's not going to stretch your stomach as much as you think. And you're going to be very, very hungry still because you don't have that stretch of the stomach. At the same time, right, or the opposite is when you have a big old meal for Thanksgiving, right? You have a whole turkey leg, and then you polish it off with a little bit of potatoes and mashed potatoes, and then some green bean casserole, and then you have pumpkin pie to just finish it all off, right? Now you have this sudden stretch of the stomach. That sudden stretch of the stomach will then, right, a much stronger stretch of the stomach will then trigger more action potentials sent to the hypothalamus, and it then will activate your satiety center. So graded means that depending on the stimulus strength, you can either hit threshold if it's strong enough, or if it's not strong enough, right, salad for dinner, you might not, right? So what else about these graded or local potentials? They can add to each other, right? Summate and add to each other. Here, you have the release of one batch of acetylcholine. It causes this little bit. And then immediately you have a second release of acetylcholine. So now, before it has a chance to come all the way down, your membrane potential from minus 70 with the first batch, it goes to minus 60. With the second batch, you're at minus 60 already. So with the second batch, right, you're going to release more acetylcholine. You might hit threshold. This is what we mean by summation right here, right? Now, local potentials spread over the plasma membrane in decremental fashion. In other words, where we release acetylcholine, right here in ligand-gated channels. Well, if you release it only in that region, right, you will then have voltage-gated, or let me rephrase that, you'll then have only acetylcholine receptors only open up in that region where you release acetylcholine. So then you'll have sodium rushing in that region only, because the acetylcholine receptors are sodium channels. As sodium rushes in, well, the region that is further away doesn't receive acetylcholine. So those receptors don't activate. So then the further we get away from where the acetylcholine binds with acetylcholine receptors, the less sodium goes in that area. So then there's a decremental effect, right? The further we get away from where acetylcholine binds to its receptor. In other words, they decrease in magnitude as they spread throughout the surface of the plasma membrane. If a local potential, when it's added and summate, are strong enough, they can generate action potentials. Usually in the brain and the spinal cord, in our nervous system, the release of one round of neurotransmitters is not enough to go from minus 70 to minus 55. it's not enough, right? Usually though, one batch of activating neurotransmitters does increase your membrane potential from -70 towards threshold to -65, right? But one batch is usually never enough for us to have it hit threshold. It makes it more likely to hit threshold, right? If something else happens, if you have another neuron releasing the same neurotransmitter, now you have two batches, right? So they add to each other. Each one goes from -70 to -60. So when you add it, that's 10 millivolt difference in each one. Now you have 20 millivolts because you have two neurons releasing, two separate neurons releasing. And then you go -70 to -50 immediately. So then you hit threshold. So we can add, and then more importantly as well, we can subtract these local potentials. And if by adding and subtracting, we hit threshold, we can then have a local potential turn into a action potential. So local potentials can turn into action potentials. All action potentials are caused by local potentials that have hit threshold and turn into an action potential. But not all local potentials are strong enough to hit threshold. So some local potentials just fizzle out, right? So right here again, if a graded potential or local potential is strong enough to hit threshold, then you'll have a full out depolarization. Voltage gated sodium channels open here, you depolarize, voltage gated potassium channels open here, and you repolarize. A large enough graded potential may cause the membrane to hit threshold immediately. When it does, like we see here, then you have a full out action potential. But, right, it sounds like it's, kind of contradictory here. All action potentials come from graded or local potential, but not all graded potentials turn into an action potential. There's an all or none principle. So no matter how strong the stimulus, right? Let's say you have a stimulus that's only 15 millivolt. It just barely hits threshold, right? That stimulus will give you the same action potential as a stimulus that is so strong, right? A 50 millivolt stimulus. There's a difference. That 50 millivolt stimulus is 3 times stronger than that 15 millivolt. Yet they trigger the same action potential. That's what we mean by the all or none. No matter how strong the stimulus, as long as it hits threshold, you will have an action potential, right? So right here, once you have an area right here that triggers and you hit threshold in this area, right? Then at the trigger zone, this postsynaptic neuron will have an action potential being triggered. In other words, you don't need to carry the action potential all the way throughout the plasma membrane of the neuron. As soon as you activate the cell will trigger an action potential along its trigger zone, which will then move it along the axon. So let's take a look. This one kind of shows right here what happens. And it's a good slide to kind of show what channels activate, what causes what. So right here at resting membrane potential, our voltage-gated sodium channels are closed, right? Our voltage-gated potassium channels are closed. Nothing's happening. We're at the resting membrane potential. Now we do have potassium leakage channels that's always open, but it's not shown here. Then what happens? Right? You have a release of a neurotransmitter. If that release of a neurotransmitter is strong enough, then you hit threshold, right? So that initial rise is that local or graded potential. If that local or graded potential is strong enough, you hit threshold, and then voltage-gated sodium channels right here start to open up. Sodium goes in, and now we have a full-out depolarization phase. Then what happens, right? Keep in mind, right? Even when you depolarize, some of your voltage-gated potassium channels open, but there's not enough potassium going out yet, right? It's offset by the amount of sodium coming in. Eventually, the sodium coming in is shut down by closure of our voltage-gated sodium channels. Now, the voltage-gated potassium channels fully open, and now potassium exits the cell, and we repolarize. Now, in neurons, we have this hyperpolarization phase, where the voltage-gated potassium channels stay open slightly too long, right? So it should be at -70, and then the voltage-gated potassium channels close. But what happens is these voltage-gated potassium channels open and stay open slightly too long, and too much potassium exits. When that happens, right, you have too much potassium exiting out, too much loss of positive charge, and you become slightly more negative than you should be. We call that the hyperpolarization phase, and usually it's caused by a hyper or after potential. And that potential means that instead of being at -70, you're at -80. At this point, right, you can still trigger another action potential, but you're at -80, not -70. So if we had a 15 millivolt stimulus and you hit threshold before, that same 15 millivolt stimulus is not able to hit threshold now because we're too negative. Now, after a few milliseconds, though, the sodium potassium pump kicks in, and we normalize our resting membrane potential from that lowered hyperpolarized state to now our resting membrane potential. Perfect. Oops. Now, let's talk about this absolute and what happens as a result of this after potential. Now, all cells that are electrical have slight refractory periods. So it's going to be becoming very important for cardiac muscles later on. But this is the first time we'll discuss it in terms of neurons, right? So what we're going to see is that these neurons undergo phases that we call refractory phases or recovery phases, right? This is the time period where that area of that axon cannot be stimulated for that small period of time. There's an absolute refractory period right here in purple, and then a relative refractory period in kind of this lavender color, right? So let's see. During the absolute refractory period, it goes from when we hit threshold to when the voltage-gated potassium channels open. What happens? Well, you're in the middle of either depolarization or repolarization. Either ways, you're in the middle of the active phases. So there's no way you can re-stimulate because you're in the middle of the action potential at this point, right? So this is the absolute refractory period. You can't re-stimulate during the absolute refractory period. There's complete insensitivity to another stimulus. And when you hit threshold right here, for that small period of time that we are either depolarizing and voltage-gated sodium channels are open, or when we're repolarizing and voltage-gated potassium channels are open. During both those phases, right, we can't re-stimulate because you can't activate those voltage-gated channels fast enough. They need time to recover, right? That's an absolute refractory period. So there's a very small time frame where that part of the axon that just got triggered, right, that just depolarized, that part of the axon needs time for the gates to close, then to recover, so then it can fully open again, right? So when either the voltage-gated sodium channels or the voltage-gated potassium channels are open, you cannot re-trigger an action potential, right? The good news is that time frame is pretty short. As soon as you hit the absolute refractory period and it ends, you go to a period of the relative refractory period. Here, with the relative refractory period, you can trigger a second action potential, but it takes a stronger stimulus. Here's the example I gave just before. If I have a 15 millivolt stimulus, that means that I barely have enough to hit threshold. What happens? I have an action potential, a depolarization, and a repolarization. But as I repolarize, I'm at minus 80 right here. That same 15 millivolt stimulus is not enough to re-stimulate the neuron or that part of the neuron when I'm in the relative refractory period. That same 15 millivolt stimulus, well, when I'm in my relative refractory period, I'm at minus 80 millivolts. So adding 15 millivolts to that just means I'm at minus 65. Too far away from threshold, not strong enough to hit threshold. So I can't re-stimulate that. Now, if I have a strong stimulus, right, what happens? A 50 millivolt stimulus, a much stronger stimulus. Instead of touching warm water, I touch hot water, right? Burning hot water. Well, if I have an action potential that's the same, if I touch warm water, I should have an action potential. If I touch hot boiling water, I should have the same action potential. So how can our brain differentiate the intensity then between warm and boiling hot? Easy, right? What happens? When you have a hot stimulus, stronger stimulus than just putting your hand in lukewarm water, right? It's now a 50, 60 millivolt stimulus. What happens? It's so strong that, yeah, that initial, you trigger an action potential. But because the stimulus is so strong, as soon as you hit the relative refractory period and you're at minus 80, minus 90 millivolts here, well, the stimulus strength is 50. So right away, it's strong enough to hit threshold. And now you have another action potential next to it. And then you hit threshold, right? Then the next action potential hit threshold because it's such a strong stimulus. You depolarize, repolarize. And then that hits the relative refractory period. And then the stimulus is strong enough for you to hit threshold again. What we are going to see is that when you have a super strong stimulus, you have the same action potential as a weak stimuli. The difference is the strong stimulus triggers more action potentials, right, in a shorter time frame. As soon as you hit the relative refractory period, the stimulus is so strong, you hit threshold again. Then you have another action potential right away. So then a strong stimulus triggers more action potentials in a shorter time frame. A weak stimulus, one action potential, and then recovery. Right? Again, that's what we're talking about here. So in terms of intensity, the frequency of action potentials allows us to interpret stimulus strength and intensity. The greater the frequency and the greater the number of action potentials, the greater the intensity, the greater the stimulus strength. So what do I mean by this? Right here. Just like I mentioned, I have touch lukewarm water. That's just a threshold 15 volt stimulus. What happens? I have enough to hit threshold. So then I have one action potential that's triggered. As I recover, right? Well, you don't trigger anymore. It's a weak stimulus. What happens if it's now a little bit warmer, right? Instead of lukewarm, it's now warm water, right? That you can bathe in. So what happens? Since it's warmer, it's a stronger stimulus than before. So what happens, right? It's now a 20 millivolt stimulus instead of a 15. What happens is you have an action potential from that 20 millivolt stimulus. As soon as you hit the relative refractory period, you have a second action potential. Tells us it's a little bit more intense now. Now, what happens when we have the maximal stimulus strength? Meaning now it's hot, right? You touch it, and if you're gonna keep your hand in it, you're gonna burn yourself. So what do? How can we tell the stimulus strength? Now this is like a 50 millivolt stimulus strength, right? What happens, right? Since it's 50 millivolts, the first time you stimulate it, it goes from minus 70 directly to minus 55, right? Easy. So you have the first action potential. As we recover from the first action potential, you hit the relative refractory period at minus 85. So what happens then? You have a second action potential because the stimulus strength is so great, 50 millivolts. You go from minus 85 to minus 55 immediately, and you trigger second action potential almost as fast as you hit the relative refractory period. As a second action potential is triggered, you depolarize and you repolarize. As you do that, you go through the time frame of the absolute refractory period. As you fully repolarize, you hit the hyperpolarized state at minus 85. Since the stimulus is so strong, you then hit another action potential, and then another one, and then another one, right? And then if it's strong enough, another one after this. So what happens is the stronger the stimulus, the more action potentials in a short time frame. Our brain interprets that as increased intensity. But keep in mind that there is a maximal stimulus strength, right? Why do we have a maximal stimulus strength? It's simple, because we can only excite once we hit the relative refractory period, right? So there's always a little time span where we have to wait before we can re-stimulate. You can't excite no matter how strong the stimulus is. You can't excite that area again when you're in the middle of an action potential, either depolarizing or repolarizing, when you're in the absolute refractory period. So you have to wait out the absolute refractory period. Once you wait it out, and now you're in the relative refractory period, then we can stimulate, right? But if you want to re-stimulate any faster, what happens is you are going to end up being in that absolute refractory period. So when you're in the absolute refractory period, you can't re-stimulate anyways, right? So there's always a maximal stimulus strength where you can't go beyond that. What do I mean? You touch molten steel, right? Or iron, and it's at 5,000 degrees Celsius. You touch boiling hot water, and it's 150 degrees Celsius. Can your body tell the difference? Right? Not really. At 150 degrees Celsius, right? Or it's like super hot, super heated steam. If you put your hand in there, it's going to absolutely burn you. You're going to trigger action potentials to the maximum stimulus strength possible. As soon as you hit the relative refractory period, you activate the pain receptors again, and then you activate the pain receptors again, and then again as soon as you hit the relative refractory period, right? That's what happens when you're at like 250 degrees Celsius. If you're at 5,000 degrees Celsius, you still have the same action potential stimulus. You still have the same frequency. Because as soon as you stimulate it, you wait until a relative refractory period, and then you stimulate again, and then you stimulate again. There's a limit to how fast you stimulate it. There's a limit to how intense that pain will feel. It's good and it's bad, right? Right. Now, propagation of action potentials. In myelinated and unmyelinated axons, we will need to propagate action potentials. Now, in an unmyelinated axon, adjacent segments activates neighboring segments. Threshold graded current at trigger zone causes action potential. Action potential in one site causes action potential in the adjacent segment of the axon. Action potentials cannot go backwards, they can only go forwards. And we'll talk about why coming up. So those are important concepts to understand, and this is probably the best way to understand it, is to really discuss this, right? So I'm going to go full screen mode, and now I have to go back to where it is. So when we're talking about this, keep in mind that we're talking about how action potentials are propagated along the axon. So here it is right here. and action potentials are propagated along the axon. And I'm trying to find my pointer. I cannot. There it is. All right. And here's what happens, right? One segment always activates the next one. So here, this segment is in the middle of an action potential. Voltage-gated sodium channels have opened. Sodium has entered. As sodium has entered, it has depolarized this region of the axon. Now, keep in mind now, sodium can, as it enters the axon, can go to the front and go anterograde, or it can go back and go retrograde, right? It can go in both directions. I just told you that action potentials only move in one direction though. Why? We'll talk about why in a second, right? Let's talk about why it goes in front, anterograde. As sodium rushes in, the sodium moves to the area that is naive. This area right here in front of the action potential, that region of the axon is at minus 70 millivolts. Is at the resting membrane potential. As sodium enters in the previous segment right here, well, sodium goes to the next segment. What happens when you add positive charge to this negatively charged segment? You make that segment more likely to hit threshold. So now it's at minus 70 millivolts. As sodium enters this segment, sodium goes to the naive segment here. So now you add positive charge to it. All right, it was at minus 70. Now sodium goes to the next segment, adds positive charge, goes to minus 60. As more sodium rushes in, goes to this segment again. Now we're at minus 55. Now as we hit minus 55, sodium goes in this and causes this segment to hit threshold. So this segment now hits threshold, and that's what we see here. As it hits threshold, voltage-gated sodium channels open. Sodium rushes in here, triggering an action potential, that depolarization caused by sodium entering. As sodium enters, again, sodium moves to the back, sodium moves to the front. As it moves to the back, it's moving retrograde. It moves to the front, is moving anterograde, and this region is at rest. It's got a resting membrane potential of minus 70. So as that sodium is triggered, right, and threshold is triggered here, and an action potential is triggered here, the sodium moves to the anterograde segment and starts adding positive charge to it. As it starts adding positive charge to it, it goes from minus 70 to minus 65. As more sodium comes in, it goes from minus 60 to minus 55. And now we hit threshold. As we hit threshold, voltage-gated sodium channels open here. And now the action potential has moved from this initial segment to this one. From this second segment, now to the third one, right? As it moves, it's going to move to the next one over here next. So with unmyelinated axons, every single segment has to undergo an action potential. You can imagine how long it would take for all those segments to undergo action potential and trigger the next segment to undergo an action potential. Now, keep in mind, I just mentioned, it only goes forward, anterograde, the wave of depolarization, only goes in one direction. Even though sodium moves in retrograde, moves backwards, right? Action potential doesn't spread in the reverse fashion. Why? It's because of this, right? Every segment that undergoes an action potential, depolarization and repolarization, every single region that undergoes that process has to undergo the absolute and the relative refractory period. And what we see is as soon as this region depolarizes, and then this region depolarizes, sodium moves backwards. But as sodium moves backwards right here, the region over here is in the process of repolarizing. It's in the absolute refractory period. So then even though sodium moves backwards, it encounters a segment that's in refraction. So you can't trigger the action potential then in reverse because the segment before it is in the refractory period. That's why it only goes in one direction. Right now, action potentials in myelinated axons also follow that same course. Right? It only moves in one direction. It only moves anterograde. Now, the big difference here is the myelination. Now, with myelination, only the bare areas is where we will see action potentials, right? So this area right here, this bare area is a node of Ranvier. We have depolarized that area, and that region is in the middle of an action potential. So now that region is activated. As sodium rushes in voltage-gated sodium channels, it goes to the next bare segment. Now, we do have some voltage-gated sodium channels, but they're very, very sparse. There's not a lot of voltage-gated sodium channels in the internode area, right? And whatever voltage-gated sodium channels we have there was covered up by multiple layers of myelin sheathing. So there's no way sodium can get through the multiple layers. So what happens? Well, we concentrate all of our voltage-gated sodium, voltage-gated potassium channels in the bare areas, or the nodes of Ranvier. As one node depolarizes, sodium rushes in at threshold, causing the depolarization. The sodium doesn't just sit still. It goes to the next bare segment. And it causes this bare segment to hit threshold. As this bare segment hits threshold, voltage-gated sodium channels here hit threshold, right? And sodium rushes in, right? As sodium rushes in, again, that's my dog snoring on me, putting my own dog to sleep. What happens then as voltage-gated sodium channels open here in the second node, right? Now I've depolarized that node, and now sodium goes to the next bare segment, causing us to depolarize the next node, and then the next node, and then the next node. Again, why doesn't it go in reverse, right? So if I'm right here and I depolarize this segment, sodium goes to the front, anterograde, it goes to the back, retrograde. How come you don't have action potentials moving in both directions? Simple. Same thing that we saw with unmyelinated axons. The region that has just depolarized always undergoes the absolute and the relative refractory periods. So as soon as this region depolarizes, it causes the next region to depolarize, sodium rush into the next region. As sodium rushes in, sodium moves backwards. As it moves backwards, it encounters a node that's in the absolute refractory phase, right? Where it's starting to become negative again, right? Which it doesn't show right here. And because of that, even though sodium's moving backwards, this segment is in an absolute refractory period. It can't get restimulated at that point. So it can only, when sodium moves to the front, that's the only time it can cause threshold to be achieved, right? Because when it moves backwards, it encounters refractory segments. And as it encounters refractory segments, it can't reactivate the voltage-gated channels yet. Right? Speed of conduction. Well, obviously, in order for us to spend that much energy to make myelinated axons, there better be a payoff. The payoff is our conduction velocity, right? So in myelinated axons, lipids act as insulation, forcing ion currents to jump from node to node. Obviously, that makes it faster to travel in myelinated axons versus unmyelinated axons. Now, when we look at myelinated axons, right, the sheathing is important. The thicker the sheathing, the faster the speed of velocity. The diameter of the axons are important, and it's all about size. The larger the size of the axon, the more room for voltage-gated sodium and voltage-gated potassium channels. Just physically, there's more room. So it makes sense that the largest diameter fully myelinated axons should have the fastest type of conduction velocity. And that's what we see here. Type A are the largest diameter, fully myelinated axon. Those nerve fibers, right, carry action potentials up to 120 meters per second. Perfect for motor neurons that are going to your skeletal muscles. Keep in mind, we mentioned the sciatic nerve previously. It's the single longest nerve in our body. So it starts with a motor neuron cell body in our lumbar spinal cord region. Then it has an axon that exits out the ventral root. Then it goes and helps form part of your lumbar plexus and your sciatic plexus. And then it helps form the sciatic nerve. And then it has to go all the way down. That axon has to go all the way down to your little toe. So then it can trigger your extensor digiti minimi to contract, right? That's a pretty long neuron. So in order for us to contract it, we need large diameter, fully myelinated axons, so then we can speed up that action potential. So motor neurons supplying skeletal muscles, and most sensory neurons, especially the ones in the peripheral nervous system, are type A, allowing us to have fastest transmission. Type B are smaller, medium diameter, lightly myelinated, and usually it's part of our autonomic nervous system. They conduct action potentials fast, but not as fast as the type A. Type C are the small diameter, unmyelinated one. These are usually interneurons. And again, right, these conduct at 2 meters per second or less. Even 2 meters per second is pretty fast, but not compared to 120 meters per second. We see this in the autonomic nervous system as well, specifically between the interneurons of the brain and the spinal cord. Again, if all we have to do is transmit an action potential a couple millimeters from one interneuron to the next, all we have to do is maybe 1/10 of a millimeter, right? Do we have to spend the energy to myelinate? Remember, you're going such a short distance. Does speed really matter? Not really. If all I have to do is to walk to the TV and turn on the TV, does it really matter how fast I'm moving? Not really. So when we're going a very short distance, speed doesn't matter as much, right? When we're going a very long distance from our spinal cord to our little toe, speed does matter, right? So we're gonna have fully myelinated, large diameter in those areas then. Perfect, all right? We will stop right here with this lecture. And, right, we will continue with right, part 5, where we talk about synapses, subnations, IPSPs, and EPSPs, right? And that will be